Hey, chemistry, and welcome to the intro videos of what I like to call Unit 0 before we begin chemistry. The beginning units are going to cover a few things like the actual periodic table, scientific notation, significant figures, and a little bit on metrics. Okay, let's begin with the periodic table. The elements on the periodic table are in order by atomic number. Now, there are approximately 117 elements on this periodic table, but you can look up some periodic tables that go to 120 elements. However, up to about right here, this is where we stop with the natural elements. So, all the elements found on Earth, 1 through 92, are natural. After that, all of these elements here, 93 plus, will be man-made. Most of them are made at Berkeley University in California and some other countries that develop new elements. Some other periodic table info is that if you'll notice that there are 7 rows as we go across here. 1, 2, 3, 4, 5, 6, 7. Those are what we call periods. And this group right here actually fits right in there. The reason that you see the periodic table like this is because we can't get it to fit on one sheet of paper. So if I were to take this part right here and slip it in there, the periodic table would really look like this. Because 57 through 71, these are lanthanides and actinides, they actually really belong right in there. Anyway, as we go across, we call those periods. And as we go down, going this way, we call those columns. Now there are 18 columns in the periodic table, and they're all numbered 1 through 18. We normally don't let the lanthanides and actinides participate in the column numbering. Mostly what we deal with in chemistry is actually going to be just the main periodic table, right up here. Okay. Now all of these groups, alkali metals, alkali earth metals, transition metals, you will get to know all of those in good time. But for right now, it's important that you know that as we go across, that is a period, and as we go down, that is a column. And there are elements are 1 through 9. One of these and blow it up. This. Each box contains an atomic number, a chemical symbol, and then, of course, the atomic mass, or what we call the atomic weight. Now, in chemistry, for right now, you will see the element name right there, but the expectation is that you learn them. So the periodic table that you get pretty much after the first 2 or 3 weeks will not have the element name written right there. All right, so the top number is what we call the atomic number. Then we have the chemical symbol, and then we're going to have the atomic mass. All right, next up is scientific notation. Scientific notation is used to express very, very large numbers or very, very small numbers in an easy way so that you can put them in your calculator. Oftentimes in science, we use really, really big numbers like meters to the moon or meters to the sun or light years away, or we can use very, very, very tiny numbers like the mass of an atom in grams is very, very small. Oftentimes, those numbers lead us to a lot of decimal places or a lot of placeholder values. And you can't put that in your calculator. You can't put 15 zeros into your calculator, 0.000 and 15 more zeros, 1, 2, to express a very, very tiny number. You have to use scientific notation. So for scientists, scientific notation, and for chemistry students, scientific notation is just another way to write a number. Scientific notation has this form. It's usually A times 10 raised to the n, where A has to be, what would you call, an integer or a whole number or a value, and n is also an integer. The difference between the two numbers is that A should be greater than or equal to 1 and less than 10. So this value right here will be a number 1 through 10. And n will be an integer and can have a positive or a negative notation. Well, let's just look at a couple numbers in scientific notation. I have 5.16 times 10 to the 6th. This number is in scientific notation. If I take 1.23, that's a 3, times 10 to the negative third, this number is also in scientific notation. This is not an exponent. This is not a value or raised to or anything like that. This times 10 to the minus third and times 10 to the 6th notate the place value that we need to move the decimal to. Now, if it is a positive number, like it is up here, this notates a very, very large number. And if I have a negative integer up here as times 10 to the minus 3 shows, this notates a smaller number. In order to expand these numbers out as real numbers, we're going to take the decimal place and move it in the direction that the exponent shows us right here. So this one says to times 10 to the 6th. So that means we're going to move the decimal place 6 places that way. So 1, 2, 3, 4, 5, 6. So this number is 5, 1, 6. And I fill in the rest of these little bumps with zeros here. So this number, 5.16 times 10 to the 6th, is actually 5,160,000. This number here with a negative integer actually just notates that the number, the decimal point is going in the other direction. This is going to be a small number. And so we're going to move this decimal place to the left 3 times. 1, 2, 3. So 1.23 times 10 to the negative third is actually 0.00123. It's a small number. Now, when you put this in your calculator, and all of you have different calculators, you're going to use a different button. And most of the time on your calculators, it looks like this. So you would put 5.16, and then you would hit the EE button on your calculator, and then the number 6, and then the enter button. We'll practice this in class. All right, moving right along here in our chemistry intro. Next up, what we call significant figures, or what I have affectionately come to call sig figs. Sig figs just represent the numbers, the digits in the actual value that you're writing down that are significant, that are meaningful. For example, if I have $1, these two zeros right here show that I do not have $1.02 or $1.03. They show when I write $1 that I have exactly $1. If I have a much larger number, like 6,500,000, all of these zeros right here are just placeholders. They're placeholders showing you that my 6 and my 5 are in the million and 100,000 place values. Same thing with the smaller number. If I have 0.012, it's not like this 0 and this 0 are really measuring anything or showing any value. They're just placeholders to show me that my 1 and my 2 are 2 and 3 decimal places back from the ones place. Now, just for a thought here, the reason that we learn about significant figures in chemistry is because really we can only have a number or a value that demonstrates to the best that we can our equipment. If you have a scale and you put something on the scale, and let's just say you're weighing chemicals here, and you put something on the scale and it says that you have 2.56 grams. That means that our scale only goes to 2 decimal places. And so we need to write that down because each of these numbers is significant. Now, if you put it on the scale and it says, and your scale says that it weighs 2.560 grams, that zero is significant. That means that our chemical compound right here was measured to that decimal place. For our chemistry students, you're oftentimes going to be given a number and have to determine what value or how many digits inside of the number are significant. The first rule to this is that all digits 1 through 9 or whole numbers, those are significant. So if I have a number that says 1,246, this number has 4 significant figures. All of those values are greater than 0, and so all of them are significant. Now I'm going to show you a shortcut for numbers such as this, or numbers such as this one that have zeros in them. And we'll do a couple of examples and using a shortcut to kind of make this a little easier on you. But just so you know where these numbers come from, we have to be able to determine in our own equipment and in our own values which digits inside of the number are meaningful and have value and are significant. So if I were to draw a very rough drawing of the United States here, I apologize, I know that you can probably do a much better job. On the left side of the United States, we have the Pacific Ocean, and on the right side of the United States, we have the Atlantic Ocean. So if you take your number, and we're just going to do our first number here, 0.000240, put it in the middle. If the decimal is present, it goes on the Pacific side. We're going to start moving this way until we hit an integer, or a value greater than 0. We hit a number. In this case, the decimal point is present, and so we stop here at the number 2, and then every number following it is significant. So this number up here has 3 significant figures. All right, let's put our next number here. 64200. If the decimal point is absent, then we're going to start on the Atlantic side and we're going to go this way until we hit a value greater than 0. And in that case, we stop here at the 2, which means that our number 1,642,000 has 1, 2, 3, 4 significant digits or significant values. All right, one more. Our last number here, 1, 0, 4, 2, 0, 0, 0, 0. Okay, our last number, the decimal point is absent. So being that it's absent, we're going to start on the Atlantic side and move this way until we hit a number. Now, this has 1, 2, 3, 4 digits that are beyond the Atlantic side. And even though that number is a 0, it's also considered significant because that's how we know it's not 1, 2, 4, 2. So in this case, we're going to count that 0 as significant, and there are 4 significant values in that number. Now, just a real quick thought, because sometimes you can see some tricky ones on a test or on an assignment. I'll let you know that, let's just say we have a decimal point that is present here. Okay, I have 0.200. That's my number. Well, the decimal point is present, so I'm going to start on the Pacific side and go this way until I hit a number. And there's my 2. And then every digit following that 2 is also considered significant. So in 0.200, I have 3 significant figures. Even though those are zeros, remember what I said about measuring on the machine? It tells us that our equipment or that our value was good and measurable to 3 decimal places. We'll practice more of this in class as well. All right, and finally, the metric system. All right, this is very important because although we don't do an entire unit on this, we used to. Back when I was in high school and took chemistry, we would do a whole unit, and you'll do a whole unit in physics on this, and if you were in physical science too, you know that we spend time on metrics. But you're going to get a little bit of just basics here. From me so that you can understand, starting with lab number 1, what it is you're doing. All right, the metric system has units of measure. All right, for mass, the units are grams. For volume, we use liters. And for distance or length, we use meters. Now these are all units of the metric system. So the units of standardized system, or what we call SI units that we don't use in science, would be things that you are familiar with, like gallon or a foot, something along those lines, or even miles. Those are units for the SI units, and they do us no good in chemistry, and we're going to avoid all of those. The basic ones that we'll be using are grams for mass, liters for volume, and meters for length, for distance. Okay, the metric system. If we have something in a substance, we need to be able to measure it. Perhaps this looks a little familiar to you. When you first used the metric system, you learned about a base unit. The base unit, right here, is what we were talking about, how we measure everything in a meter and a gram or a liter. That is our base unit. So I'm going to write at the top, let's just say I have 1 gram of something, salt. All right. Now, if you remember the mnemonic, King Henry died by drinking chocolate milk what this helps you remember is the abbreviations of the metric system: kilo, hecto, deca, deci, centi, and milli. And we're only going to use so many of these in chemistry. I'm not telling you this to be tricky. I'm just letting you know. It's hard for me to say, go weigh out 0.00046 kilograms of something. That would not make any sense. But sometimes we have a scale that measures in grams, or we have a scale that measures in milligrams. And so you need to be able to convert between the two and understand the differences between the two. So let's just say I ask you to go measure something that's one gram. And you go pick up your scale, and your scale is measured in milligrams. You know, it's right over here. So if you put 1 on top of that scale, you're not going to get the right measurement. So if I ask you to go measure something out, 1 gram of salt, and you pick up a scale and it's in milligrams, you need to be able to convert 1 gram to milligrams. And based on where it's at in our system here, you would move the decimal point over however many place values you're going to. So if I want to go from grams, which is right here, to milli, which is over here, I am 1, 2, 3 places over to the right, which means I would take my 1, and the decimal place is normally right there, and move it over 1, 2, 3 places to the right, and fill it in with zeros. So 1 gram is equal to 1,000 milligrams. So you would go get your salt and put it on the scale and weigh out 1,000 milligrams, and that would be the same thing as 1 gram. I also wouldn't say, go get me 45 liters of something. And just by the way, I use a cursive L for liters. It just helps me, keep what I mean by liters different from milliliters or elements on the periodic table. So I just use a capital letter for liters in cursive. So if I have 45 liters of something and I want you to go get something to measure it out, you might pick up the equipment, and the equipment will only have it in kiloliters. So how many kiloliters of this am I going to need? Well, here's my base unit. My base unit of liters is right here, and I'm going 1, 2, 3 places over to the left. So on my number 45, the decimal point is really right there. If I want to go from liters to kiloliters, I move it over 1, 2, 3 places to the left. So 45 liters is equal to 0.045 kiloliters. And really in chemistry, you're going to see everything in kilo or in a base unit, and we use a lot of milli. So being able to go back and forth between the place values is important. All right, my wonderful chemistry students, thank you so much for watching your first intro video. I hope that makes unit 0 labs and unit 0 videos a little bit more helpful here as we proceed and as you do your first couple of introductory activities. All right, I look forward to a great semester.